We will follow some selection rules in order to get the allowed transitions in UV visible spectroscopy. Not all the transitions are possible to observe. Some of the transitions will be called to be the forbidden transitions, which will not fall in UV visible range, or these happens at a so much lower intensity level that they cannot be observed in UV visible spectroscopy. There are some forbidden transitions which may be sometimes observed, and these are due to the some other factors. And all these selection rules will be applicable to explain UV visible spectroscopy, and forbidden transitions will not appear in the final spectra. Similarly, we would get a band structure in case of visible spectroscopy. While in all other techniques like IR, we get some peaks, sharp peaks there, and they elucidate the structures. In similar case, for example, in case of NMR, we take sharp peaks, while in case of a UV visible, we have a band rather than a sharp peak. Uh, because the molecules is in the form of the solution in case of UV visible spectroscopy. The sample is in the form of the solution, so vibrational and rotational energy states are affected by that solution interaction, and we would get a energy band or a band spectra instead of the sharp peaks here in case of visible spectroscope photometer. This band structure arises due to the superimposed energy levels, and these superimposed energy levels are transitions at very low energy levels which are affected by the solution. For example, these all energy levels, whenever the transition would take place in so close energy levels, which appears to be the band spectrum. These closely spaced energy levels would arise, would sum up to give a energy band, not sharp peaks here in the case of UV visible spectroscopy. UV visible spectroscopy, the main principle is of Beer's law. The later on, after some modification, it will be called as Lambert's-Beer's law. The based upon the absorption of the light by the sample, we have an equation dpx over px is equal to ds over s. Dpx is the intensity or the power of the radiation absorbed, px is the incident radiation, will be equal to ds is the number of molecules which are absorbing the radiations, and s is the total number of the molecule. And this ds, the total number of absorbing molecules are absorbing area, will be equal to total number of molecules, or will be directly proportional to total number of absorbing molecules. So ds may be taken to be equal to adn. Here a is a constant, dn is the number of particles which are absorbing the radiation. dpx over px would become equal to adn by placing ds equal to adn here in this equation number 1. We have another equation like dpx over px is equal to adn over s. Integrating this equation within the limits on left hand side between p naught to p and on right hand side from 0 to n, we get a final equation as log p naught over p is equal to an over 2.303 s. Area S can be described by the volume. In terms of volume, it will be equal to V over B, where B is the path length, V is the volume, and it would become equal to the area S. Substituting this value in equation number 4, we get log P naught over P is equal to A N B over 2.303 V. Here, N over 2.303 V are the constants, and these all constants are taken to be equal to C, and we would get the equation as log P naught over P is equal to ABC, or it may be called to be absorbance is equal to ABC. Here P naught is the incident radiation power, the radiations which are incident on the molecule, and P is the radiations after emitting from the solution. And we may convert absorbance into transmittance by this one method, transmittance is just the reciprocal of the absorbance. Absorbance is equal to minus log T, and minus P over P naught may be taken as a absorbance. A is equal to ABC or equal to KC. It means that A and B remains constant, and just absorbance depend upon the concentration. Greater the concentration, greater will be the absorbance. Lower the concentration, lower will be the absorbance. So it is an excellent tool in order to explain, in order to check the solutions quantitatively. We may take or observe the concentration of the solutions. Unknown concentrations can be found by using Lambert's Beer's law and spectrophotometers. These are different terms. These are the terms which are modernly used, and these are the terms which were used classically. For example, radiant power P, P naught were taken to be I and I naught. Absorbance, say optical density, it was known as optical density. Transmittance was known as transmission. Path length B were labeled as L or D values. Absorptivity A was known as extinction coefficient. Similarly, molar absorptivity was named as molar extinction coefficient. In modern literature, all these terms are used, while in case of the classical literature, you would use the term, you would read the term in the case of intensity, optical density, transmittance, etc. Beer's law, when applied on the mixtures, the total absorbance will be equal to the sum of the absorbance values of all the molecules in that mixture, and extinction coefficients E1 for the species 1, BC1, similarly for the species 2, E2, BC2, etc. are taken. If these extinction coefficient values for all the species are equal, then simultaneous determination would not be possible. These are the assumptions taken for the Lambert-Beer's law. Incident radiation should be monochromatic. Absorber molecules should be identical and should act independently. Similarly, incident radiation are parallel, and these are incident perpendicularly on the surface of the sample. Similarly, path lengths traversed or path length moved by the radiation through the solution will remain same for all the radiation, mean all the radiation would cover an identical path length through the solution will be exposed. Absorbing medium is homogeneous to all the radiation, and it does not scatter the radiation. It will be assumed the incident flux means the total number of radiations passing through a unit perpendicular area will remain same, and it should not cause any type of the saturation there. There are some deviations from the Beer's law. Instrumental limitations are there: resolution, signal to noise ratio, satellites, etc. There are some sample limitations as well: molecular interactions, associations, hydrogen bonding reaction, refractive index changes, etc. These are some limitations or deviations from Beer's law will be explained later on. Chemical equilibria, whenever we would apply UV visible spectroscopy on a solution at equilibrium, where reactants and product molecules are at equilibrium, then if E is different for both reactants and products, then absorbance would depend, and we would not get a plot between absorbance, and total absorbance will not be linear. So it may also be applicable on the chemical equilibrium reactions. Thank you, students. It was all about today. You may ask some questions if you need. Thank you. Assalamu alaikum.